Today I'm going to talk about aluminum beams subjected to impact loading. I will talk about how material properties can affect the response, how the mass ratio between the impactor and the beam can affect the response, and also how welding can change the response or affect the response. First, I will talk a little bit about the bad and good points about aluminum as a structural material. Then I will say something about aim and scope of this talk. I will give you some short introduction to impact mechanics, and then give some basic assumptions for the work I'm going to present. I will introduce to you to moment curvature relationships and moment second moment of area. I will say something about force displacement curves, local buckling of a compression flange in a thin wall beam, tension failure on the tension side. I will then introduce to you to something called mode approximation technique linked to energy absorption, and then some validation of the work, and then I will also at the end say something about what happens when you weld an aluminum beam. And then everything what I've presented is then gathered in a spreadsheet. We call it PLCA program. So I will give some at the end some few examples. Aluminum, the bad points. I suppose you know that aluminum costs much more than steel. But if you have a structure and if you have a 50% weight reduction by using aluminum instead of steel, the price for the aluminum structure is more or less the same as for the steel structure. But remember, then you have a 50% weight reduction. Effect of temperature, aluminum weakens more than steel, which can of course be a problem. We have a link to buckling, elastic modulus, it's lower than steel. And also this have effect on deflection. We have, when you weld aluminum, you have a heat affected zone where you have a reduced the mechanical properties locally, which can affect on localization of strains when you have large deformation of a structure. Fatigue limit is lower, and then also the thermal expansion is twice as much as steel. So why do we use aluminum? Well, the good points is that low weight has huge impact on what happens in the automotive industry today. We have an electrification and the battery is quite heavy, and then you need to reduce the body weight of the structure. And then aluminum is a chosen material. For instance, if you have the extrusion process, you can extrude a cross shape, which you design on your own, for instance. It's quite cheap to extrude. Recycling, it's very efficient that when you recycle a material, you use approximately 5% of the energy needed to produce primary aluminum. And 75% of the aluminum today is recycled, as I understand. You have low temperature performance, so when you go down in temperature, then you increase the fracture stress, increase the fracture strain, and so on. It's non-rusting, machinability, and also good energy absorption capability. So if you look at specific energy, for instance, which is the energy absorbed divided by the mass of the absorber, it's much better than steel. So that's why you, or also today, for instance, have bumper crush box system in aluminum. So I can give an example here. This is an Audi TT. And the body cell weight here is 206 kilos. By introducing aluminum here, you say that you're able to reduce the body weight by 48%. And you see that you have only steel at the rear part here. The rest is castings, sheets, and the blue is extrusions. And I can tell you that also in this new Audi e-tron, there are approximately 800 kilo aluminum. And in the oil and gas industry, there is also a lot of aluminum, living quarters. This is a tension leg platform, it's floater, and definitely the weight on the top side is critical. And to reduce the weight, you, for instance, use aluminum. I will not go into more detail, but this is a very interesting material in the offshore oil and gas industry. So the aim and scope of this is to study the behavior of aluminum beams subject to impact loading. Focus is placed on support conditions, cross-section geometry, impacting mass and velocity, as well as material properties. If you know the design code, Eurocode 9 for aluminum structures, all cross-sections are in class 1 and 2. This is linked to the BOT ratio of the element composing the cross-section. And the energy absorption here is linked to material failure on the tension side and local plastic buckling on the compression side. And then I will also show the effect of welding. So first, a little bit impact mechanics. This is a picture that I got when I took my PhD in 1980 worked on my PhD from 84 to 88, 1988. This is a gravity platform, and you see here you have drill pipes lifted on board by cranes, and if one of the drill pipes is dropped, then it can penetrate the deck structure. So here is the projectile I studied in my thesis. It's a drill collar, 3,200 kilo, can be dropped from heights up to 50 meters. And how to study the deformation? At that time, we had only one camera, high-speed camera. We had to use 120 meters of film. We have not a video camera at that time. And to study the movement or deformation of the plate here, when impacted, we used some pins with some crosses, and then we were able to film the crosses and study the movement. And here you see what happens. This is at time t equals 0, and then you see that the pin starts to move as a function of time. And at time 1.1 milliseconds, the disturbance or the wave has moved all the way to the supports. And here is also some numerical simulations done in the 80s. And you see clearly that you have a circular disturbance which is moving towards the supports. Actually, this was done by on LS Dyna, done by John Hallquist himself when he was working at not LS Dyna but Dyna 3D, when he was working at Livermore software at the lab at Livermore before he started his own company. So. This is the force time curve. This is the force between the plate and the impactor as a function of time. The first part here is where the plates, where the support does not record any forces. At here, the forces, the supports are fully activated. And if you transfer this into force displacement curve, you see that here the supports are fully activated. So a lot of energy is absorbed in the transient phase of the impact. And here you see that the mass ratio between the target plate and the impactor was 0.28. If we now increase this mass ratio to 0.55, you see that a dramatic change in the force displacement curve take place. Here, the supports are fully activated. So most of the energy absorbed in the plate when you can remove the supports. And definitely you need systems to calculate this. You can do it by a computer code, but it's also interest from an engineering point of view to also have some tools which you can use to design a beam or a plate subject to impact when you take this into account. But as you see, a lot of energy is absorbed. The dotted line here is the corresponding quasi-static curve. And this is where you get plugging in the plate. So if you take a beam and impacting mass, then you can calculate that the strain, that the energy, kinetic energy in the plate is absorbed as strain energy in the plate and multiplied by here a correction factor to take the transient phase into account, where we then use the mode approximation technique, which I will present to you later. We then looked at simply supported beam, clamp beam. I have a rectangular horizontal section, and from this, I can very easily generate this by moving these two webs together, and I can also study the behavior on H-beam. So I can very easily, by having this, study the behavior of 3 different cross-sections. What I did to calculate the force displacement curve here is that I assume that the total strains are additive. The elastic and plastic strains are additive. And I also assume that this is the relationship between the plastic strain and the plastic curvature, same for the elastic strains and elastic curvature. And by introducing this into this, I can say that the curvature, total curvature, is the sum of the elastic and plastic curvature. Then we have the material. Here, this is typical for aluminum. I'm using a power law, which is the relationship between the stress and the plastic strain. K here is given like this, and this is the so-called Ramberg-Osgood equation. This is the elastic strain, this is the plastic strain. And the nice thing with this is this N determines the hardening of the material. So if N is very big, you have an elastic, perfect plastic material. And then if N equal 25, which is more or less for a T4, then you have this, and this is for a T6. And this is a formula which is used in the design code for aluminum structures. So N here is 1 over M. So the moment curvature relationship is like this. Here, plastic, elastic, curvature, and then we have the moment. So assume that you go up and then you unload like this. Oh, the moment, let me see, moment curvature relationship. Here is the moment in a cross section. Stress times Z times dA integrated over the cross section. And then I can introduce for sigma, I can introduce for EP, then I get this term. And then I can integrate over the cross section. And then you see that I'm able to get an expression where moment in a cross section is a function of the curvature and the material properties and the cross-section geometry. This is a term that I want to use in the future. And then for the elastic part is approximately the same, and I can obtain that the well-known term that the elastic curvature is the moment times elastic modulus and the second moment of area. Second moment of area is, you see here, very easy to determine, and then you can get impressions for I-beams and H-beams. How to calculate the force displacement curve? Well, I use the principle of Wheeler complementary work or Wheeler forces, which says that this is the external Wheeler force, this is the internal work, and then you have an equilibrium, and then you keep the displacement constant, and then you vary the forces, which means that you also vary the stresses. And then I can then introduce E here into this equation, I get this, and then I can integrate over the length and cross section, and then I get 2 terms. I get this term, which is the last from the elastic part, and this is from the plastic part. And here we know that this is then also a function. This is the external moment, which is a function of this. So this will be deleted. And then you will able then to find that the total displacement is the sum of the elastic part and the plastic part. The elastic part is something that we know very well. So I will now calculate this for a simply supported beam. This is the plastic part. This is the Wheeler work. This is the Wheeler moment. Here is the moment diagram. And I will not go into detail, but this is then the plastic deformation, which you see again is a function of M, which is a material property K, and the cross-section geometry. And the elastic deformation is like this. So if you shall calculate now, for instance, the force as a function of displacement, you have to do this numerically because it's impossible to solve it directly. So you have to introduce this in here, this here, and then you have to then do this numerically. Find the relationship between force and displacement. Then you can also very easily calculate the plastic strains, which is important. And in the outermost fiber on the tension side, in the midsection, the maximum plastic strain can be given like this. But we can also calculate the plastic strain as a function of x along the beam, which is interesting, because you will see that the material properties has huge impact on how the strains in the beam will localize. And this is an advantage of aluminum, because if you want a certain material, you can change the properties by heat treatment. So for a clamp beam, it's more or less the same. I will not go into detail. We can use the principle of Vector forces, sorry. Here is the assumed moment diagram. And the moment is given like this. The vector moment is variation of m is given like this. And then we can then get this term here, and which is introduced here. And this is the elastic deformation, which you can find from a textbook. It's very easy for a clamp beam. I'm not taking any actual deformation into account, it's only bending. And again, the plastic strains. What's interesting here, the plastic strains in the beam as a function of x. So then we have been able then, hopefully I will show later how this is validated, to generate the force displacement curve. And for an aluminum, we know that when you have high strength aluminum, often you use that because it's beneficial with respect to energy absorption. You reduce the hardening of the material, which means that you reduce the ductility. And I will show that. But we can also, on the compression side, we can have plastic buckling. And I will show a method based on J2 deformation theory of plasticity. So this is the total strains. This is the effective stress, effective strain. I will not go into detail. I will say that this is the second modulus of the material. And I will now assume that when buckling takes place, the plate is here in the compression flange is straight before buckling and is subjected to only compression stresses. And I assume that when buckling takes place, there is no unloading. And if you take an example from a column, for instance, it's based on the tangent model theory. And this is the Shanley theory. And this is the reason why we have two buckling curves in Eurocode 9, because the tangent modulus is a function of the hardening of the material. The Poisson ratio is assumed as 0.5. And what we assume is that the plates are compressed and that the stresses and the non-linear material properties vary from their pre-buckling values. This is very important. So it is now assumed that buckling will occur if equilibrium state changes character, at which another equilibrium state is possible. You have an equilibrium and then it starts to bend and then you find a new equilibrium. If that's the case, then the plate has buckled. And then the buckling equation is given like this. Seems quite complicated, but it's not. It's the variations in the moment, x, xy, and y, and also the normal forces acting on it. Who did this? I have not developed this theory, but this theory was developed by National Advisory Committee for Aeronautics in 1948. It was before they had the computer. They need to do hand calculations. And if you have a rectangle hollow section like this. And if you look at the compression flange up here, we can model it as a plate, simply supported plate, long simply supported plate, and it's subjected to stresses like this. And then these guys found out that the critical buckling stress is the elastic buckling stress times a correction factor, taking plasticity into account. The elastic buckling stress is given like this, and this is the correction factor. And now you see that this correction factor is a function of the secant modulus and the tangent modulus. And the tangent modulus is given like this. The secant modulus is given like this. When looking at this formula, you clearly see that when you are going to do a numerical simulation and you have folding, buckling of thin wall components, you clearly see that it's totally wrong to use a bilinear stress strain curve. You need to be able to be very careful to quite accurately model the hardening of the material. This is very, very important. If not, you can get a totally different deformation mode. So this is for a simply supported plate. This is for an outstand. An outstand is this. It's a flange supported along 3 edges. This edge is free. Again, we have this formula here. This is the elastic buckling stress. K is a factor which is dependent on the support conditions and so on. But you see that in this case, the plastic factor here is only a function of the secant modulus divided by the elastic modulus. So for a simply supported plate, it was both a function of ET and ES, but here it's only a function of ES. I suppose that some of you will, when you have a beam subjected to impact in the center, you have a gradient in the moment, which means that you have variation of the stresses in the flange. I'm not taking this into account here, because this, what I'm showing you now, is a conservative estimate. And I also don't take, for instance, in this case, I don't take any continuity into account. In the design codes, you always assume this as hinged. Yeah. So if we plot these formulas now for outstands and for simply supported internal elements, this is the buckling curve. This is the slenderness B over T, and this is normalized critical stress. In the design code for aluminum structures, they are not allowed to pass this stress here. So we're not allowed to have higher stresses than the 0.2 stress. But you see that if you have a quite thick or low slenderness or quite thick profile, then definitely there is some extra capacity here, which you need to take into account. So take, for instance, now, I don't know if you are used to use this, if you know how to use this or are familiar with the Eurocode 9 design code, but you see that this is for internal elements. You have different curves, and these curves are a function of the hardening of the material, how the shape of the stress strain curve, and this is for outstands. So we have here 3 curves, not only a function of the hardening of the material, but also a function of if you have welding or not. But because welding will introduce imperfections and residual stresses, which will have impact on buckling. Then we go to the tension side. And how shall you do that? Because how can you do this in a very simplified manner? Well, we have been using, for instance, forming limit diagram like this. If you have a sheet stretch in 2 directions, you know that this is the diffuse necking curve, because here is rho, here is the ratio between the two strains, and here is the strain in the principal direction. And here is the localized necking curve. And in a flange, you are very close to plane strain. You have strains in the bending direction of the beam, but the strains are very small in the opposite direction. So this is a conservative estimate. And then we see that this value here is 1. And then localized necking coincide with the diffuse necking when rho equal 0. It's very easy, because if you have a stress strain curve like this, it's very easy then to calculate that when you have determined M, you then have an value which gives you when localization takes place, and then we say that game is over in the beam. So back to the mode approximation technique. This was first proposed by Martin and Simmons. I think Simmons, he was a professor at Brown University in US, and this was first published in the 60s. And if you look at this figure now, we know that if you have a stress and the E dot are lying here, and if you have any other admissible state of stress here, sigma star, we know that this term is always positive. This is due to Drucker's stability postulate. If now, for instance, this sigma star lies on the yield surface, then we can put up this, because this sigma star is associated with E dot star. And these two equations can then be combined into something like this. This has to be positive. And then these two guys, Martin and Simmons, they utilize this to come up with something very simple. When you have a structure subjected to, for instance, impact, we say that two solutions can be found which satisfy the field equations. We see that we have solution 1, we have a velocity, we have an acceleration, we have a stress, and then we have a strain rate. Then solution 2 is associated with U dot star, acceleration star, stresses star, and strain rate with a star here. But the velocity field is often chosen on a modal form given like this. So this is a time function, this is a shape function. Then they put up using the vector velocities. And it is assumed that when the tractions, inertia forces, and stresses of each solution here is in equilibrium, because this can be put up by vector work, the difference in these quantities are also in equilibrium. So this is the difference, this is the inertia term, this is the strain stress term. So if we now further take this, play around with this a little bit. This is the term, and then we define a new function delta. And if we take the derivative of delta with respect to time, we end up with this. But from equation 3, this is positive, which means that the derivative of this has to be negative. And this implies that the difference between the modal solution ui star dot and the actual solution does not increase with time, but they are approaching each other. So this delta function is less than the initial function at time t equals 0. And I will show now examples how to utilize this, because you have then an actual solution. This is the real solution, and this is an approximate solution. And I will show how to utilize this to make your calculation quite simple. This is an example of a cantilever. Have a mass at the end, impacting mass, and it can be solved if we assume a rigid perfect plastic material, that in the transient phase you have a velocity field like this, and you have a hinge moving towards the support, and this is the global or model solution. So if you take the exact solution and plot it, here is the velocity of the tap as a function of time, and this is the exact solution. The mode approximation solution is this one. So we see that the two solutions are equal at some time, and they are equal from the time when this hinge has reached the supports. I can tell you that to do these calculations, it will take you 1 day. It's quite heavy. So from an engineering point of view, it's quite hopeless to do. So you need something simple. Even to put up a numerical simulation can take you a lot of time. So at least this can be used as a first approach using this mode approximation technique. So how do we use this? Well, here we have a beam, simply supported beam. This is the real velocity field. At impact, we have only velocity in the center, and this is the mode velocity field, where we assume a velocity field like this at time t equals 0, where this velocity at the center is different from this velocity. And now I use this formula here at delta at time 0. This is the actual field, extra velocity, and this is the mode field. This and this is the mode field, where this is known, this is the shape function, this is the unknown. And then I can introduce this here, and then I can take the derivative of this with respect to this and minimize the difference between the real solution, real velocity field, and the mode field. And this is given here. And then you see that I get an expression for VIO bar. And by doing some calculations, I can find this expression that this term here, bar, VIO bar, is equal VIO divided by a term which is linked to the mass ratio between the beam and the impactor. How do you utilize this? Well, my initial kinetic energy now is linked to this system. And I can then put up the kinetic energy for the impactor, the kinetic energy for the beam, and I can introduce this. Then I get a term like this. So the kinetic energy, which has to be absorbed, is this initial kinetic energy multiplied by a factor, which is a function of the mass ratio between the beam and the impactor, which makes the calculation quite easy. Then I get rid of these one-day calculations. So what do we have? Well, we have this. We have kinetic energy, which has to be absorbed as strain energy in the global mode phase. This has been programmed because there is a lot of equations in the spreadsheet. We are not assuming any rate effects. They are neglected. And I'm also will show you what happens if I introduce a weld, cross weld at the position here. Norman Jones, he has a book called Structural Impact, an excellent book for people working with impact dynamics and plasticity. And he has an example where he has a clamp beam subjected to dropped object or falling mass at the center. He has defined the transient phase. This is a velocity field and global mode field. And he has an exact solution for the displacement like this, where you see that again, this is a function of the mass ratio. And you assume a moment theta rotation relationship like this. Now we have compared this solution with this mode approximation technique. When you are going to compare, he has a perfect plastic material. So here we need to put E equal very large, almost infinity, and then we need a large value n. So we have a almost elastic, perfect plastic material in the spreadsheet. And here, this is the Norman-Jones solution. This is the displacement. It's dimensionless as a function of the mass ratio. And this, the black curve is the exact solution by Jones. And mode approximation technique gives you this. Yeah. So very good comparison. If you want to be a real engineer, you don't use this mode approximation technique. You say that, for instance, you have a clamp beam, and you have a dropped object, you have the kinetic energy, which is then absorbed as plastic energy in a hinge shear, and hinge shear. Then you can put up this, and then you can do like this and plot it, and then you see this is the line here. So when the mass ratio is 1, you definitely get a very conservative solution. So if you want to be a little bit more accurate, which maybe can be the case for you, then you should, for instance, try to use this mode approximation technique. We have also done some comparison between this mode approximation technique and numerical simulations. You will also find a lot of comparisons in the literature, but if you now first look at the force displacement curve based on the principle of vector forces, this is for a simply supported beam. This is for a clamp beam for a material in T4 where you have the yield stress. The N is equal 8, and you see that the abacus solution and this PLCA solution is more or less the same. We have also done the simulations with shells, and you see that here is a shell solution now, and you see that here we got buckling in the using the formula from NACA, and here approximately we get buckling in the abacus simulation. And this is the same for a T6 alloy, where the yield stress is 250 and equal 25. Still, the force displacement curve is well represented, and we are not so far from the analytical model gives quite good predictions of when buckling takes place. We have also done some studies linked to comparison, linked to impact. Here is the ratio between the abacus displacement and this simplified model using mode approximation technique as a function of mass ratio. And for a tempered T4, T6, we are within plus minus 10%. So from a design perspective, this looks quite promising. If we now introduce a cross weld, then we have a challenge, and this is something that people do not know, because if you have two plates which is welded together, you have a weld you see here, but you have a heat effective zone. And if you take this stress strain curve, which is obtained from a small specimen out here, then you have a stressing curve like this. But as long as you're moving towards the weld, you see that you lower the yield stress and you change the hardening. And you see that in the heat affected zone close to the weld, you have a curve like this. So for this alloy, which is an 6082 T6, you lower the yield stress by 50% by moving from the material out here to what happens in the weld. And when you stretch this, this will definitely have impact on how localization will take place and how your structure will behave subjected to an impact. Again, done we have put up some formulas linked to using the virtual forces. We have a weld here done for a simply supported beam. This is the base material, and this is the properties in the heat affected zone. So we then give in the length of the heat affected zone and the position. Yeah, quite heavy calculations, but here a nice thing with these calculations I show now is that you have control over the parameters. So this can be used in design, of course, but this is also for the students to learn which parameters count or not. This is very, very important because when you do a numerical simulation, you don't see anything, you see a black box, but here you can understand the effect of mass ratio, the effect of material properties, and so on. So then I will show you the spreadsheet. Maybe I can go out of this. I need to go out of this. Started this again, hopefully. If I can. No. So not this one. Well, maybe I should share screen instead. Hope you see this. Yes.
Yes, it's perfect.
Yeah. So this is a spreadsheet. And what's interesting here you can look at simply supported clamp plates. This is the cross section. We can then have static dynamic loading. We can include acceleration of gravity, and we can include welding. And here I have an example where I have a height 300, 200, thickness of the flange is 20, web 15, which means that we are in class between 1 and 2. I have a T6, where the yield stress is 250, N equal 25, Young modulus is 70 gigapascal, and the density. And here, now I will first turn out the weld, impacting mass like this. And then I can do a calculation. Then you see, here you see the plastic strain along the beam. And here you see the stress strain curve. And here you see the force acting between the impactor and the beam. And if you look at this, we see that here is the load situation I've chosen. And here I get diffuse or localized necking, which is the red dot. And here I get buckling of the rectangular hollow section profile in the compression flange. So here it seems to me that everything's fine. What's interesting here, the estimated plastic localization strain is 1/n, and this is then 4%. And you see that here I have approximated 3.5%, and I have a displacement of 175 millimeter totally. So if I now change this to, for instance, T4, then I can have, then I had 225. I reduce the stress because it's lower, and then I have 12.5. Then you see that the spread of the plastic deformation is increased along the beam. Now the strains are much lower. Here's the localization strain, but here you see that I have challenge with buckling. So, but if you now, for instance, have a material where the hardening is almost zero, let's take 250, and then you take an N which is 1000. Then you see everything localized in the center. And if you look at the strain you have, EP load. You have 155% of strain. And definitely here, this you will never be able to reach this. Which means that when you have a material which is almost elastic, perfect plastic, the chance for localization and large strain is quite high. If I now again go back to this, and then introduce a weld like this, then the weld has the same properties as a T4. This is the hardening exponent. The length of the heat affected zone is 40, and the total length of the beam is 3 meters, so the weld is localized here. Let me first skip this, then we can see. Here you see everything looks fine, and of course, then a guy is coming to you and say that, okay, maybe I should introduce a weld here. It will maybe work. I introduce here. Now you see what happens. I get a very strong localization in the weld, and the strain in the weld is 25%. So if you will not have any problem with what happens in the center, but fracture will take place in the weld because you have a strong localization due to the fact that you have a small zone where you have reduced the material properties or yield stress. But you have increased the hardening, of course, but this tends then to localize all strains. And this is one of the challenges with aluminum, that when you weld, you have to be aware of where you put the weld compared to the deformation of your structure. So yeah, I think that this ends my talk